To perform one iteration of gradient descent algorithm, we have to compute the gradient of loss function. But this is very heavy process. We need a lot of computations to obtain the gradient value or gradient vector. Why? Because in machine learning process with n number of data point, when you have n training data point, the gradient essentially is sum of each loss function of data point. Here xi denotes the ith element of your training data, and yi is the ith element of your output label, and theta t is the parameter that define your machine learning function. Well, precisely each L function I have explained in the previous videos. This can be some so in that case I use this notation. This is some function defined with a parameter theta with input xi, and we will measure the distance between the output of your function and the true label yi. So for the classification task, we can use cross entropy. For regression task, we can use L1 norm or L2 loss function. So when there are n number of data points, we have to define n different functions, and we have to compute n different gradient vector. So this is very huge computation, and in machine learning and in deep learning training, we usually have a lot of training data point, millions or billions of data point we have. Okay, so we usually do not compute the exact gradient value. We do not compute the gradient, but we compute the stochastic gradient. So then what is the stochastic gradient? Stochastic gradient is the stochastic or random vector such that, so this is, let's say this is gt. This is stochastic or random vector such that the expectation of gradient of expectation of gt is equal to gradient of your original loss function. Okay. And also the stochastic gradient vector is very easy to compute. That's why we use stochastic gradient instead of gradient vector. Okay, and one very easy approach to define such stochastic gradient vector is mini batch based stochastic gradient descent. Essentially, at each time we randomly sample B set and just sum over the randomly sampled set B and then compute the gradient. So, of course, the gradient is with respect to theta. Since we randomly choose the xi and yi pair from entire data point, the expectation of this with respect to the random sample process will equal to the full gradient, which is called full batch gradient. Okay, So this is very nice approach to define stochastic gradient. And when you use this stochastic gradient descent algorithm, you can make a very efficient algorithm. Okay, at each iteration, instead of computing n gradient vectors, you just need to compute just a b gradient vector, cardinality of b gradient vector. Okay, then what is the good size of the mini batch? So this is called a mini batch. So what is the good size for this mini batch? This is a very interesting and important question. When you increase the size of B, basically at each time you can compute more accurate estimation on full batch gradient. But computational complexity also increase because you have to compute more gradient vector. But when you decrease the number of sampled vector, then although you can save the computation time, the error for the estimation on the full batch gradient will also increase, which can cause oscillations or divergence of your update. Okay, so you have to very carefully choose the size of batches, the size of each mini batch.